Okay, I will start the class soon. Okay, so for those who haven't signed your attendance, please fill up the form. Okay, all of you have filled up the form, so I will start the class now. Okay, today I will continue with another new topic. Okay, this is chapter 5. Okay, also our the lecture 5. Okay, I consider as chapter 5. Okay, chapter 5, there are 3 parts. Okay, you will learn about the MOS inverter. The MOS inverter here. Okay, let me check. Okay, chapter 5 focus on static characteristic. Okay, static characteristic here means the DC characteristic of the MOS inverter. Okay, MOS inverter here means that the inverters that is uh, make of make from the transistor. Okay, the two transistor, NMOS and PMOS. Okay, inverter can be CMOS inverter and also NMOS inverter. Okay, so these two type of inverter I will cover today. Okay, NMOS and CMOS inverter, these two inverters, they have different performance. Okay, so under chapter 5, I will discuss about the DC characteristic. Okay, DC characteristics here, what I mean is on the voltage and current characteristic. Okay, the voltage usually I will cover on the input and output. Okay, what are the effect and also the threshold voltage. Okay, as introductions to the most inverters, for any IC technology used in digital circuit design, the basic logic gates elements is the logic inverter. Once the operations and characterizations, okay, I heard, not sharing, I'm sharing now already. You all cannot see. Okay, let me reshare again. Okay, how about now? Okay, now only I see that the screen is shared to you all. Okay, so now should be okay. Okay. Okay, so just now I mentioned about the chapter, what this chapter 5 cover. Okay, chapter 5 cover about the MOS inverter. Okay, the MOS inverters here cover the NMOS and the CMOS inverter. Okay, inverters are made of NMOS and PMOS. Okay, um, for NMOS inverter, it means that this inverter is actually composed of only NMOS. Okay, so the um, characteristic that will be studied and discussed in these chapters for the most inverters will be the DC characteristics. Okay, so okay, I goes to these introductions. Okay, just now I mentions that for any IC technology used in digital circuit design, the basic logic gates element is the logic inverter. Okay, if we want to construct a logic circuit, in a logic circuit, the fundamentals, logic component is logic inverter. Okay, so that's why I emphasize and I focus on these fundamental logic components. Okay, in this course, okay, because this is the fundamental. Okay, and then if you learn about the types of the logic inverters, then you learn that in the most technology or IC technology, okay, there are a few. Okay, there are a few of the um, constructions of the circuit that we can apply in most technology. Okay, to construct the IC. Okay, so once the operations and characterizations of an inverter circuits are truthfully understood, the result can be extended to the design of the logic gates and other more complex circuits. DC characteristics of various MOS inverter circuit can be examined, okay, using positive logic in conversions. The logic values of 1 can be represented by a high voltage of VDD, and logic value 0 can be represented by a low voltage. Okay, so the circuit that I will demonstrate to you later, okay, all are in voltage level. Okay, so for any high voltage level of VDD, we consider it as logic 1. Okay, as for low voltage, it will consider as logic 0. Okay, okay. On studying the DC characteristics of the inverters, it means that to study the voltage, okay, voltage characteristics of the inverter. Okay, so as you see that this is the graph. Okay, the graph is plot with V out versus V in. Okay, we call this as DC voltage transfer characteristic. Okay, in short, we can call it as VTC. Okay, this one you must remember, VTC. Okay, is a voltage transfer characteristic of the ideal inverter circuit. Okay, so how should we interpret this graph?
Hello, Miss.
Ah,
Sorry to
yes.
interrupt. Your screen stuck at slide number 1.
Uh, means that
Now moving already.
okay. Okay, so this is the VTC graph. Okay, VTC graph. How should we interpret this graph? Okay, this graph is V out versus V in. Okay, so for any input voltage, okay, that is to the inverter, will cause a change in V out. Okay, so this is an inverter. All of you know the operations of an inverter. When the input voltage is high, then the output voltage will be low. Okay, is inversely is proportional. Not sorry. The input and output is inverse. Okay, so when the input voltage is high, okay, output voltage will be low. Okay, and otherwise. Okay, so so you see that in this graph, when the input voltage is low, okay, this is a low voltage. Consider low voltage level. Okay, when the input voltage is low, then the output will be high. So the out here, you see the voltage level here is high output. Okay, if the input voltage is high, okay, then the output voltage is low. So you see the line here, it means that the output voltage is low. Okay, so this is how we should understand the graph. Okay, remember this graph is for ideal inverter. Okay, and logic 1 output, logic 0 output. So you know what is meant by this. Okay, because of high and low output voltage level. Okay, for any input voltage between 0 and threshold voltage, okay, VTH here means the threshold voltage. Okay, this is the minimum voltage where the voltage is considered high. Okay, minimum voltage. Okay, so the threshold voltage is given as VDD divided by 2. Okay, the output voltage is equals to VDD logic 1. Okay, the output switch from VDD to 0 when the input is equals to VTH. Okay, so if you refer back to this graph, so it means that this is the VTH. Okay, at this voltage level, okay, when this input voltage, okay, is above the threshold voltage, then the output will change. Okay, output will change. At this point, at this threshold voltage, okay, the output is still high. Okay, but above VTH, then it consider high voltage. Then the output will change. Okay, the voltage VTH is called the inverter threshold voltage. Okay, for any input voltage between VTH and VDD, the output voltage assume a values of 0. Thus, an input voltage 0, uh, is it the screen again? The slide. Or you cannot see any things that are drawing on the slide and pointer. Okay, how come? Yeah. I think next time I use my laptop is better. Okay, how about now? If due to the PC lagging, so maybe you can see now or slideshow. Okay. Okay, how about now? You see all the slide and the writing. Okay, wait a minute. Yeah. Can you- Okay, I'm sorry about that. I'm testing on something. Uh, okay. Let me check. How is it? Patch 3. Okay, I will reshare again. Okay, how about now? This is page 3. You can see already. Okay. Okay, give me a moment. I am opening up my another laptop. I need to see your message, okay, so that I know your problem later when I am giving the lecture. Okay, a very quick one. So give me some time here. Okay. Okay, so I will continue with this slide. Okay. Thus, an input voltage. I will continue with this statement. It is about the range of the input voltage. Okay, so the input voltage here, the range given is 0 to the threshold voltage. It is between the 0 to the threshold voltage. Okay, so it is interpreted by this ideal inverter as logic 0. Okay, while an input voltage that is between the threshold voltage and the VDD is interpreted as a logic 1. Okay, so this one, you refer to the graph, then you will see, okay, which one is logic 0 and which one is logic 1. Okay, and the DC characteristics of actual inverter circuit will obviously differ in various degree from the ideal characteristics. Okay, next I will mention about the VTC of a realistic and most inverter. Okay, this is one type of an inverter. Okay, it is the realistic one. Okay, later I will show you the VTC of a realistic and most. Okay, but now you need to remember for a VTC of an ideal inverter, the shape is look like this. Okay, this is the shape of an ideal inverter. But later, for realistic and most inverter, the curve will be a bit different. Okay, it's similar, but there are some difference there. Okay, later I will show it. Okay, so this is a NMOS inverter. Okay, why it is called as NMOS? Because there is only NMOS transistor in this inverter. Okay, no PMOS. Okay, no PMOS, and this is a load. Okay, this load usually it is a resistor. Okay, this is a resistor. Okay, so this we call it as NMOS inverter. This circuit also can work as a inverter. Okay, as you see that the circuit here is almost similar to the ones that we know. Okay, with VDD, Okay, VDD output and input. Okay, so here the input is also called as VGS. Okay, it means that the gate to source voltage. Okay, why it is called as gate to source voltage? Because this is a gate terminal. Okay, this is a source terminal and this is a drain terminal. Okay, it consider the voltage that measure at the terminal. Here, the gate terminal to the source terminal. Okay, this we call as the input voltage. And then the output voltage. Okay, output voltage we also call it as a drain to source voltage. Okay, drain to source voltage. Okay, why it is drain to source? Because the voltage is measured from the drain terminal, okay, at this point to the source terminal at this point. Okay, so this is V out. Okay, at the output voltage point, okay, there is a capacitor. Okay, C out. C out is a capacitor. Sometimes you call it as a load capacitor. Okay, and here there is a resistor. Okay, resistor, we can select a few of the resistance. Okay, this resistor will affect the shape of the VDC. Okay, and the resistor here will have some, when there is a resistor here, of course there is a power dissipations, and depending on the input voltage to the NMOS, okay, the amounts of the current flow will be different. Okay, it also has different. Okay, so later I will talk about the operations of this circuit. Okay, now this circuit is to show it to you which one is input voltage and output voltage. Okay, and then there is another uh, voltage. Okay, we call it as VSB. Okay, if you see this VSB, this is a substrate. It's not substrate, sorry, it is source to the substrate voltage. Okay, means that this, okay, I change the color. Okay, I don't want to confuse you. Okay, this, you see this line with the arrow here, this is VSB equals to 0. Okay, and then the load device, there is a terminal currents, IL. Okay, it means that the currents flow from the VDD to through the resistor. Okay, with IL. Okay, this is load current. Okay, we call it as load current also. Okay, and then terminal voltage or the load voltage. Okay, if you see VL, it is means by load voltage. Okay, so I go to the next slide. Okay, the terminals of the load device is connected to the drain of the N channels MOSFET. Okay, while the other terminal is connected to the VDD, and VDD is the power supply voltage. The output terminals of the inverter shown in figure 5.3 is connected to the input of another MOS inverter. Consequently, the next circuit seen by the output node can be represented as a lump capacitance Cout. The typical VDC of a realistic NMOS inverter is shown in figure 5.4. The general shape of the VDC in figure 5.4 is qualitatively similar to that of the ideal inverter transfer characteristic shown in figure 5.2. Okay, however, several significant differences deserve special attention. Okay, so I show the figure 5.4. So this is the VTC of a realistic NMOS inverter. Okay, you see the shape here. Okay, at the slope here. Okay, this slope and this slope. Okay, it is actually not a shape. It's not a sharp transitions. Okay, the transitions happens here is very slow. Okay, it's very slow because it is a realistic inverter. So to make the transitions, it will take some time to transit from high output to low output. Okay, so ideal one is look like this. Okay, ideal one. So just now I have shown to you before, it is like this. Okay, so in realistic, the difference here is the slope. Okay, this is the realistic VTC. Okay, again in this VTC, it is also plot with V out and V in. Okay, in this V out and V in, we need to determine the level, output voltage level. Okay, there are two output voltage level here. This is a high output voltage. Okay, VOH here means the output high. Okay, means output high or high output level. VOL means the output low. Okay, this is how we can understand the graph. Okay, and then for VIL, okay, VIL, this is for the input. Okay, input low. Okay, and then this one is the threshold voltage. Okay, this is the input high voltage. Okay, when I say input high, input low means that it is referred to the voltages. Okay, and then this is a voltage level. This is also an input voltage. Okay, input voltage, but it is equivalent to the VOH. Okay, means the voltage level is equivalent to the high output voltage. Okay, sometimes VOH is VDD. Okay, if let's say VOH is 5 volt, okay, it means that here maximum input voltage allowed is 5 volt. Okay, if VOH is not given, okay, if VOH is not given, okay, only given with VDD 5 volt, then we should know that this VDD is also the VOH. Okay, straight away we know how to label the graph. Okay, so this is the meanings of the label here. Okay, for all the voltages. Okay, here already given to you the definitions for VOH, VOL, and input input law. This is VIL and VIH. Okay, VOH means the maximum output voltage when the output level is logic 1. Okay, and VOL is the minimum output voltage when the output level is logic 0. Okay, and VIL is the maximum input voltage which can be interpreted as logic 0. Okay, why it is a maximum input voltage? Okay, if you see the graph here, okay, at this point, okay, the input is still considered as logic 0. Okay, okay, but if the voltage increase to above VIL, then it is not logic 0. Okay, it is not logic 0. That's why VIL is the maximum input voltage which can be interpreted as logic 0. So for this region, okay, any of the input voltage that is below the VIL, it is considered as logic 0. Okay, and then for VIH, okay, VIH is the minimum input voltage, which can be interpreted as logic 1. Okay, so you see the graph again. Okay, the graph here, this is VIH. Okay, this VIH, when the voltage to the input of the NMOS is at VIH, and the input is considered as logic 1. Okay, so this is the minimum voltage. For any voltage level that is above VIH, it is all considered as logic 0. Okay, I draw here. Okay, this is logic 1. Okay. For very low input voltage level, the output voltage Vout is equals to the high values of VOH. In this case, the driver NMOS transistor is in cutoff and hence does not conduct any current. The voltage drop across the load device is very small in magnitude and the output level is high. As the input voltage Vin increases, the driver transistors start conducting a certain drain current and the output voltage eventually start to decrease. The drop in the output voltage level does not occur abruptly, such as the vertical drop assumed for the ideal vertical VTC, but rather gradually and with a finite slope. We identified two critical voltage points on this curve where the slope of the Vout characteristic becomes equals to -1. Okay, the slope here is defined as d Vout divided by d Vin. Okay, this is the differential function. Okay, differential functions indicates the slope in the VTC. Okay, so the slope is equals to -1. So you see this graph. Okay, the slope is at this point. Okay, this is not the slope. Okay, the slope you see -1 is the slope for the VTC. Okay, there are two slopes. Okay, and then about the statements given here, let me see. Okay, so I should refer back to the circuit then. Okay, so the statements here, it means two conditions. Okay, the conditions when the input voltage is low, okay, then the output is high. Okay, output will be high. Okay, so when the input to the NMOS is low, means that NMOS is in cutoff. Okay, NMOS is in cutoff. Okay, and then no current is conduct. Okay, means that I use back this circuit. Okay, I need to use back this circuit. Okay, so just now is about low input voltage. Okay, and then this output is high. Okay, and then this transistor is cut off. Okay, cut off, and then V out here will be equals to VOH. Okay, why it is equals to VOH? Because the output here, okay, if it will refer to here, the VDD, okay, the VL, the load current, there is no current conduct, okay, no current conduct, okay, and then the voltage drop here is also small, okay, so the output here, the level, the voltage level here is at the level of VDD. Okay, and then when the input is high, okay, then there will be current conduct, okay, through the load, okay, and then there is also a voltage drop through the load, okay, and at the output will be small. The output will depends on the currents flow through the NMOS, okay, from drain to the source. Okay, the smaller input voltage value satisfying this condition is called the input low voltage VIL. And the largest input voltage satisfying this condition is called the input high voltage. Both of these voltages play significant roles in determining the noise margins of the inverter circuit. Okay, as the input voltage of the first inverter is further increased to equals to VIH, a logic 1, the output voltage of the first inverter continues to drop and reaches a values of VOL corresponding to a logic 0 level. Okay, for this one, okay, this is actually refers to another figure. Okay, let me see. Is it? Okay, just now the slide is referred to this figure, figure 5.5. Okay, this figure, as you see that there is a 3 inverter here. Okay, 3 inverter, okay, that uses the realistic NMOS inverter. Okay, in reality, we should also consider the noise, okay, the influence of the noise to the signals transmissions. Okay, so this figure is actually to show how to understand how the noise margin is determined and how it should be understand. Okay, based on the figure here given. Okay, if you see this figure 5.5, okay, the inverters, the first inverters, this is the first inverter, okay, and this is the second one, and this is the third one. Okay, and the first inverter here, the input initially is high input, and then the output is low. Okay, and in between here, there is a wire. Okay, this is labeled as interconnects. Okay, and then when the signal is transmit from the output to the input of the next inverter, okay, there will be noise from the environment. Okay, the noise can be any noise. Okay, the noise, coupling noise. Okay, so this one, the noise should be the noise that can be tolerant by this circuit. Okay, in order to achieve the in order to make sure that the signals, the voltage level of the signals, okay, is at accepted level. Okay, if it is not accepted, means that the result that we obtain at the output will be different. Okay, it will be not correct. Okay, so later the explanations, the slide, I will go back to the previous slide. Okay, it is about this figure 5.5. Okay, so this is the statements about the input voltage of the first inverter increase to equals to VIH, and then the output voltage continues to drop and reach a values of VOL. Okay, so this is the output of the first inverter. And then the inverter threshold voltage VTH, which is considered as the transition voltage where V in equals to VL on the VTC. Okay, there's a total of 5 critical voltages, VOL, VOH, VIL. VIH and VTH characterize the DC input-output voltage behavior of the inverter circuit. The functional definitions for the first 4 of these critical voltages are described in figure 5.4. Okay, so just now I already show you the figure 5.4. Okay, so now I will explain to you what is meant by noise margin. Okay, based on the figure in 5.5. Just now I show you with the 3 inverter. Okay, the ability of an inverter to interpret and input signals within a voltage range as either a logic 0 or as logic 1 allows digital circuit to operate with a certain tolerance to external signals, perturbations. Okay, this tolerance to variations in the signals level is especially valuable in environment in which circuit noise can significantly corrupt the signals. Okay, the circuit noise corresponds to unwanted signals that are coupled to some part of the circuit from neighboring lines by capacitive or inductive coupling or from outside of the system. The result of this interference is that the signal level at one end of an interconnections line may be significantly different from the signal level at the other end. Okay, to illustrate the effect of the noise on the circuit reliability, consider the circuit is consisting of 3 cascaded inverters. Assume that all inverters are identical and the input voltage of the first inverter is equals to VIH. Okay, the output voltage of the first inverter will be equals to VOL, corresponding to a logic 0 level. Okay, this output signals is being transmitted to the next input of the inverter through an interconnect, okay, which could be a metal or polysilicon line connecting the 2 gates. Since on-chip interconnects are generally prone to signal noise, the output signals of the first inverter will be perturbed during transmissions. Consequently, the voltage level at the input of the second inverter will be either larger or smaller than VOL. If the input voltage of the second inverter is smaller than VOL, these signals will be interpreted correctly as a logic 0 input by the second inverter. On the other hand, if the input voltage becomes larger than VIL, it may not be interpreted correctly by the inverter. Thus, VIL is concluded as the maximum allowable voltage at the input of the second inverter, which is low enough to ensure a logic 1 output. Okay, consider the signal transmissions from the output of the second inverter to the input of the third inverter. Assuming the second inverter produces an output voltage level of VOH, these output signals will be perturbed because of the noise interference, and the voltage level at the input of the third inverter will be different from VOH. If the input voltage of the third inverter is larger than VOH, these signals will be interpreted correctly as a logic 1 input by the third inverter. If the voltage level drops below VIH due to noise, the input cannot be interpreted as logic 1. Consequently, VIH is the minimum allowable voltage at the input of the third inverter, which is high enough to ensure a logic 0 output. Okay, so the slides here mentions about the voltage level at each of the inverter. Okay, so I will refer back to this figure 5.5. Okay, so you can read back, okay, and refer to this figure 5.5. Okay, it is actually means the signal level. The signal level can be corrupted by noise. Okay, can be corrupted by noise, and then the voltage level, it can vary. Okay, can vary to below VIL or above VIL. Okay, since this inverter should produce high output, okay, if the input voltage it is above VIL, so it should consider to produce correct output. Okay, sorry, I think I say it wrongly, not correct. Okay, this is VIL input load. So any of the voltage level that is below VIL or at VIL, okay, it can produce correct high output. Okay, so if the input voltage, okay, there are some noises added into the signal, and then the voltage level change to be higher, and it is higher than the VIL, so it means that it will produce a incorrect output. Okay, incorrect output. Okay, why is that? Because the output will become logic 0. Okay, this is not what we want because the output is supposed to be a logic 1. Okay, so that's why this VIL is the maximum voltage allowed at the input of the inverter. Okay, so the noise margin is about how much the voltage can be fluctuated, okay, within the given voltage. Okay, the values, okay, the voltage values, how much the value can drop again and then increase. Okay, we have to make sure that the output that is produced is correct. So for the third inverter, also the same concept. Okay, you can read back and then to understand. Okay, to understand the operations of this whole circuit. Okay, I see that I only have 5 minutes. I think I'm going to end, but I will cover one more slides here. Okay, so the observations leads to the definitions of noise tolerance for digital circuit called the noise margin. The noise immunity of the circuit increases with noise margin. Okay, when we want to know, okay, whether this circuit has good noise margin or not, okay, we can evaluate it through it is whether high noise margin or low noise margin. Okay, if a circuit has a high noise margin, means that it is good performance. Okay, we say it is with good performance because it can sustain um, a high fluctuation of noise, okay, and is immune to the noise. Okay, so if the circuit is with low noise margin, so means that the circuit is very susceptible to the noise. Okay, the specifications most commonly used to describe the noise margin uses two parameters. Okay, low noise margin, it is NML. Okay, you see this term, okay, this is means by noise margin. L is low. Okay, and then high noise margin is defined as NMH. Okay, so when you are asked to find these two noise margin, low and high noise margin, uh, you can use the formulas given here. Okay, low noise margin is VIL minus VOL. Okay, and high noise margin is VOH minus VIH. Okay, so later I will explain this one. Okay, it is related to these formulas given. Okay, so due to the limited time today, I will continue this on Wednesday. Okay, So far, is there any questions from you, okay, about this topic? Okay, no questions. Then I think we can dismiss class now. Okay, for students who will be having tutorial later, okay, you need to stay back. Okay, so I will end the lecture class now. Okay, thank you.